Hello and welcome, class, to Chapter 11. Chapter 11 is all about gases. So we are not totally getting away from thermodynamics. We will be talking about like enthalpies and heat exchanges in the next couple of chapters. Chapter 11 is all about gases. Chapter 12 is all about liquids and solids. And we're going to round out everything in this particular unit with phase changes, how one particular phase transforms into another. All right, so let's not get ahead of ourselves. Let's talk about pressure, what it means to be a gas, and the early gas laws. All right, so as we get started in this chapter, I will disclaim that I am doing things out of order from the text. Primary reason is it always comes down to this. I don't like how the textbook's organized for this particular section or conversation, so I am doing this in rough chronological order. It makes more sense to me to learn about gases in the way that they were first discovered and studied back in the 1600s and 1700s. So what inspired us to start studying gases in the first place? The atmosphere around us, really. The atmosphere as we understand it today is a, relatively speaking, thick layer, relative to us, thick layer of gases, primarily made of nitrogen, oxygen, carbon dioxide, and argon that helps to keep us not only protected from the solar radiation, but also gives us the air that we need to breathe. Now, relative to the size of the planet, the atmosphere is not actually that thick. So we can see the planet, on the left. If we were to take the planet, cut it in half, the thickness of the atmosphere is only about as thick as the apple skin is on an apple. Thickness. So to us, the atmosphere may seem pretty tall, relatively thick, abundant around us, but proportional to the entire planet, the atmosphere is actually pretty thin and it's relatively fragile. So it's one of those things that we tend to take for granted, and it's very important that we keep in mind not only the importance of the atmosphere, but how small it is in the grand scheme of things. Our story begins with, I'm going to butcher this name, Evangelista Torricelli. He is an Italian physicist. We would call him or consider him in part today to be like a meteorologist. He cared about studying the atmosphere. He was inspired by the air around us to discover what it was made of, what were its properties. And so Evangelista Torricelli was working in the early 1600s. We can see his birth and death years here. Torricelli's greatest accomplishment, at least the one that we're going to be talking about, was the invention of the barometer. Now, the barometer is an instrument that is used to measure atmospheric pressure. Most barometers nowadays are some form of digital instrument. You can't really see the mechanisms that are going on the inside of that box. But his original barometer was way simpler than that. You could construct it with 3 pieces, basically. First, you needed a long tube, which we can see here. It looks like a very long test tube. That's basically literally what it was. He filled this test tube with liquid mercury. Now, mercury was more often used in chemical experiments during this era. Not only was it relatively abundant, but its properties actually lend itself to being useful for a great number of chemical studies. For instance, here we're going to be talking about pressure. Another really useful property of mercury allowed it to be used to test conductivity. And it's it just really comes down to the fact that mercury is a liquid metal. Metals are super useful in technologies due to their consistent behaviors, ease of electronic flow. And mercury is even more useful because it is a liquid, so we can get some really nice malleable properties out of it as well. All right, so what Evangelista did, what Torricelli did, was took this test tube of mercury, carefully inverted it, tipped it over, inverted it into this bucket of mercury or bowl of mercury, this separate container. And what he witnessed was that the mercury inside of this tube would fall a little bit, which is what led to, or results in us seeing this kind of blank space up on top. Now, if you're not being very careful with this type of experiment, you could lose some mercury, which could be where this empty space comes from. But if you're being really careful to not lose anything from outside of the test tube, like if you seal it, dunk it under, and then take the stopper out, you're still going to get this little bit of a blank space, this empty space up on top. So the first discovery that Evangelista Torricelli made was that vacuums existed. Vacuum being technically defined as an area of truly empty space, right? There's no particles inside of this vacuum. It's particle-less. Believe it or not, that used to be a contentious thought, whether or not you could have truly empty spaces, or if there had to be some type of particle or force field inhabiting that space to make it actually allow it to exist. So Evangelista Torricelli supplied some pretty strong evidence for the existence of the vacuum, and not only that, but we can see that the mercury inside of this tube did not completely fall down into the bowl. So we do have two competing forces here. The first is the force of gravity, right? The weight of the mercury pulling it down the tube, which is what resulted in this vacuum in the first place. The other competing force, though, comes from an upward force in this tube. And the upward force in this tube results from the bowl around it interacting with the atmosphere. You see, the atmosphere is made up of hundreds of thousands of millions of quadrillions of gaseous particles. And Evangelista lived in an era where they didn't actually know that, but his experiment provided some pretty strong evidence for it. You see, if the mercury is being pulled down by gravity, well, who's to say that all of these other invisible particles are not similarly being pulled down by gravity? So if there are particles in the atmosphere, it stands to reason that they're going to have some type of weight to them. And their weight is what is pressing down into the mercury surrounding in this bowl. Well, since we have so much weight being pressed down on the mercury in the bowl, there's nowhere really for this mercury to go except for up. So we have these two competing forces, the atmosphere pressing down into the bowl, and the mass of the mercury, the gravity of the mercury pulling it down in the test tube. And what we end up seeing is that the atmosphere is winning a little bit. Like, the atmosphere is so massive, there's so much weight to it, that it's able to press or push or shove this mercury up into the test tube. And it's able to maintain this relative height. The term pressure, which is what we can use to describe this behavior of the atmosphere, the ability for all of these gaseous particles to press down on the mercury, was first coined by Blaise Pascal, also in the 1600s. Blaise Pascal also confirmed Evangelista Torricelli's findings with his barometer, and also found, on top of that, that the atmospheric pressure seemed to decrease with altitude. If he was at sea level, right in Italy, sea level next to the ocean, the height of the mercury remained constant. Like, no matter how many times he inverted this mercury test tube into the bowl, this height right here remained the same. If he climbed up a nearby mountain, however, what he found was that the height of this mercury inside of the test tube fell a little bit. He associated this with a lesser mass of the atmosphere itself, so if there's not as much mass here, if there's not as much weight on the bowl, we don't have as many competing forces, not as much of the mercury is going to be pushed up into the test tube, which allows the gravity of the mercury to take over and it will fall a little bit. So he saw that there was this altitude dependence, and he rationalized that this has to do with how much weight in the atmosphere is able, or does exist above the barometer. So this barometer was useful for measuring atmospheric pressure specifically. Now, pressure is defined as the quantity of a force applied to an area. So Blaise Pascal took this discovery one step further, right? It's not just that the atmosphere had mass, as Evangelista Torricelli discovered, but also that this particular mass, due to the fact that the atmosphere is made of gases, is able to apply what is technically known as a pressure onto that surface of mercury in the bowl. So pressure, we can say quantitatively, again, is a force, which is represented by our variable F, per area, which is this capital A. And according to Newton's second law, force is equal to mass times acceleration. So whether or not we are given like a force directly, or if we're given a mass and some type of like gravimetric acceleration, we're able to approximate or calculate what the pressure is of the atmosphere at any one given point. Like how much pressure is actually being applied to objects down on the surface of the planet. So something that's really cool about the pressure of the atmosphere, kind of flashing forward to our modern understanding of it, is we can think of the gaseous particles that push down on us almost in like a column of air directly between us and outer space, right? Like how much pressure is being applied to you as a person standing is not the equivalent of all of the gaseous particles in the atmosphere, but rather if we consider you as a person standing on the planet, the only air that we need to consider pressing down on you is the air that is directly above you in this sort of like cylinder space. So if you were to hold out your hand, this introduces a new little like section of space that we're considering, right? If this is your hand here, we're only going to observe how much gas is directly above your hand. Well, the mass approximately of air that is above your hand providing atmospheric pressure to your open palm is approximately 100 kilograms. 100 kilograms, to give more of like a visualization, is approximately the equivalent of 40 textbooks. So as you're holding your palm out, and I invite you to do so now, the mass of air in the column above you that provides atmospheric pressure against your open palm is approximately 40 textbooks, right? And we have this pressure, this mass of air pushing down on us all the time, and we don't even realize it because we're so accustomed to its feeling. All right, so since we're starting to quantify pressure, let's talk a bit about the units. Because pressure and gases, like atmospheric gases in particular, were studied over such a wide period of time, really like, again, the 1600s all the way through the 1800s, and large discoveries were kind of like consistently being made every like so many decades during this time period, we have many different units with which to define pressure. The standardized unit nowadays, the SI unit, is the Pascal, named after Blaise Pascal, who coined the term pressure in the first place. A Pascal is a derived unit, right? It's not one of those 7 fundamental units that we've already introduced in the fall, which include time, length, the candela, those types of like fundamental units that can't be broken down anymore. The Pascal is a derived unit, which means it is comprised of other units. So the Pascal is technically defined as 1 Newton divided by meters squared. If we want to really break this unit down though into the fundamental standardized SI units, the Newton is equal to a kilogram meter per second squared. So this is how we get this fundamental unit over here, or this fundamental combination of units over here to the right, where a Pascal is equal to 1 kilogram per meter second squared. The Pascal, though, again, is not the only unit that is kind of comprehensively used. There are so many other pressure units that are more readily used as opposed to the Pascal. So the most common unit for pressure that is used here in America is the atmosphere. The reason why is 1 atmosphere is approximately 1 atmosphere's worth of pressure. Like, it's the average pressure that you feel just kind of walking out into the world. 1 atmosphere of pressure we can see is equal to 101,325 pascals. So it's also a fairly large unit compared to what the standard SI unit is. Another unit that's very commonly used is 1 millimeter of mercury, also known as 1 torricelli. This unit in particular is pretty readily used in Europe since it is named after Torricelli, the man who started this all. We can see that 1 millimeter of mercury, also known as 1 torricelli or 1 torr, is equal to 133.322 pascals. Last but not least, we have the bar. The bar is the standard unit used by the International Union of Pure and Applied Chemistry. So this is the formal standardized chemical unit, 1 bar. It is approximately also equal to 1 atmosphere, but we've rounded off a little bit so we can see that 1 bar is technically equal to 10 to the 5th pascals. Moving forward, as we begin working with through some example problems pertaining to pressure and atmospheres and chemical experiments in particular, we're going to be seeing any one of these units used. Pascal, atmosphere, torr, or bar. These are pretty common units, and so we're going to have to get used to these unit conversions. We're going to be using them a lot in this chapter. So here we have our first example problem of the day. I think it's actually a pretty neat problem to consider, since we're oftentimes focused on, the atmosphere and gases on our planet. Let's consider the atmosphere or gas particles on other planets, specifically the moon Titan. So the mass that we have found of the atmosphere on Titan is pretty large, 9 times 10 to the 18th kilograms, and its surface area is 8.3 times 10 to the 13th meters squared. So overall, the atmosphere is fairly massive, and the surface area we can see is also a very large number. This makes sense. This is a planetoid after all. I would like you guys, though, to calculate the atmospheric pressure in atmospheres for Titan. So here we have the acceleration given at the end of the problem. What this acceleration is equal to is the acceleration of gravity on the moon for Titan, which is, here we can see, equal to 1.35 meters per second squared. This is definitely smaller, less of a gravity than what we have on this planet. So the atmospheric pressure may end up being a little surprising. So I'm going to give you guys the chance to kind of digest what we've talked about, calculate this atmospheric pressure in atmospheres yourself, pay attention to the units, and we will compare our work in a moment. All right, I hope the problem went well. If anything was confusing, hopefully working together will help illuminate any source of confusion. All right, so we're asked to find an atmospheric pressure, pressure being represented by variable P. Here we can see in the problem, we have a mass, we have an acceleration, we have a surface area. So what equation better to use than pressure is equal to mass times acceleration, all divided by surface area. All right, so I'm going to rewrite that over here so I have space to actually work. Pressure is equal to the mass of the atmosphere, which is 9.0 times 10 to the 18 kilograms. We're going to take this and multiply it by the acceleration, 1.35 meters per second squared. And we're going to divide all of this by the surface area of the planet, which is 8.3 times 10 to the 13 meters squared. So again, what we're doing here is taking the mass, how many gaseous particles there are, multiplying it by the acceleration, how quickly these things are not only moving, but changing direction. This gives us literally the best idea, the only real way to calculate how much force each of these little particles is applying. And the surface area then is telling us how much of this force is being applied per every unit of area on the planet's surface. All right, so the calculation ends up equaling 1.5 times 10 to the 5th. And if we're paying attention to units, which we should, we can see that kilograms are going to remain in the numerator. The meter is going to be canceled out by a meter down below. So this meter is going to cancel. The squared is going to cancel. So we have a meter down here. And the seconds squared remain as well. Now the seconds squared are listed in the numerator currently, but we can also see that they're technically in a denominator. So algebraically, we can take the seconds squared and drop it down into the literal denominator that remains. And we can see our unit is a kilogram per meter second squared. Now you're asked to find the atmospheric pressure in atmospheres. What we currently are working with is the definition of the Pascal. So what we're going to have to do is take the Pascal, convert it into the unit of atmospheres. So we're starting with 1.5 times 10 to the 5th pascals now for our last step in the conversion / calculations. So our Pascal is going to be converted into the unit of the atmosphere by dividing by 101.325 pascals per every 1 atmosphere. This gives us a final pressure of 1.48 atmospheres. So the planetoid, since it's a moon, right, is smaller than our planet, but the atmosphere is so thick, despite the fact that the acceleration of each of these particles is smaller than that on our planet, there's so many particles that the atmospheric pressure ends up being a little bit greater than what we would experience here on our planet, where the average pressure is 1 atmosphere, pretty much no matter where you go. And now we enter probably my favorite area of this pressure conversation. And the reason why is we are now entering the era and focusing on the scientists who were, at the time, considered to be either alchemists or physicists, but nowadays we would consider them to be the fathers of chemistry. We are seeing the birth of chemistry as a study in this chapter. Where we're starting now is with Sir Robert Boyle. He considered himself primarily to be an alchemist. So this is before chemistry was even a quantifiable field of study. Alchemy was just as esoteric as it was exoteric, so there were a lot of spiritual components that were considered in the study of alchemy. Things like what the phase of the moon was, and what the positions of the stars were, and I mean, all of that kind of stuff. What tide, like, was the tide high or low? So there were the seeds of the scientific method being planted. Like these scientists, these natural philosophers really didn't know what variables they should or should not be paying attention to, what things actually mattered. So they paid attention to everything. Robert Boyle is the first of the fundamental scientists, the first of our fathers of chemistry that we consider here in the Western world. What was Sir Robert Boyle studying? Of course, he was studying the atmosphere and gases. Namely, he was really invested in what the vacuum was, right? Evangelista Torricelli discovered the vacuum. It was a pretty contentious discovery because there were so many natural philosophers, theologians, scientists who were of the sound mind that there needed to be something in order for other stuff to travel through it. Namely, if light were to travel through a space, there needs to be a medium for it to travel through. So vacuums were thought to be ridiculous. Sir Robert Boyle wanted to understand them. He thought that the experimental evidence for their existence was pretty strong and sound. So he hired Robert Hooke, who was, by modern standards, a physical engineer, to design a vacuum pump for him. So we can see there's this gaseous chamber up on top. This is where stuff would be put. So like, for instance, one of the things that he put in his vacuum chamber was a candle. And the mechanisms down below would basically pump the air out of the chamber until we were pretty close to like 0 pascal. So very, very low pressures inside. Not necessarily a true vacuum, but as close as we could get in the 1600s. So Robert Boyle put a fair number of objects inside of this vacuum chamber, and basically everything that happened was the exact opposite as what he expected. And again, his hypotheses were founded on what he understood alchemy to be. So for example, both the barometer and the candle, as well as like the small animals conversation, are all wrapped up in the same thing. That according to the alchemists, there were 4 major elements: fire, earth, air, and water. And each of these elements, according to alchemical properties, got in the way of the other elements. So barometers, which were made of mercury, were thought to be predominantly made out of the element of water because it was a liquid. Boyle's rationale was, well, if we're pumping all of the air out, that means that we're pumping all of the element of the air out. And this means that the water component of the mercury should be able to expand, right? It should be able to take up more space because the air is getting out of the way. But it actually turns out that the barometer and the mercury level inside fell. We understand nowadays the mercury level fell because of the decreasing pressure, but Robert Boyle was like, that's weird, it should have risen because now there's more room for all of the mercury. Candles, same thing. Because candles, namely flames, were made of the element of fire, he assumed that removing the air from the vacuum chamber would allow the fire to expand, because it would have more space to expand into now that the air was gone. But the flame extinguished. Small animals, he assumed that, just like us, the atmospheric pressure was a burden for us. If we could remove that burden, if we could remove literally the weight from our shoulders, Shouldn't the animals placed inside of this vacuum chamber, like, thrive? Would they not just be happy at this, like, reduced pressure on their shoulders? Turns out that the animals suffered. And nowadays, again, we understand that, like, we need air to breathe. They did not quite understand what the connection was between breathing and the gaseous particles that we needed to survive. I will say, though animals, yes, were harmed in these projects, we do not have on record that any of these small animals died. So, and this was in an era where, like, death was also seen to be a key alchemical component. If there were to be death, it would have been recorded. So we can, you know, rest assured that even though some animals were harmed in the making of these experiments, none, it seemed, at least on record, died. All right, the next things that we can talk about also are kind of in the same vein. Like, if you're removing air, wouldn't, light not be able to move through the vacuum? Turns out that magnets and lights worked just fine. However, all sound ceased. So if you put a metronome or some type of, like, sound-making device inside of the chamber and pump all the air out, we can't hear the sound anymore. And then last but not least, liquids when placed inside began to bubble and they would disappear. So all of these results were totally counterintuitive to what Sir Robert Boyle thought would happen, but are totally consistent with what we understand nowadays. So of course, like, this is the starting point. These experiments were the starting point for us to be able to understand how gases actually function. In 1662, Sir Robert Boyle concluded his observations from using this vacuum pump in one pretty concise statement, which is now known as Boyle's Law. The particles of remaining air, having more room to extend themselves in, will less press out one another. Now that is the Old English way of saying, if you expand the volume, as we can see here, if we expand the volume, you are allowing the particles to extend out, right? They're able to spread out, and as a result, will less press into one another. As you expand the volume of your container, the particles have more space and therefore have a decreased pressure. And the opposite is also true. If you push down on the lid of this container that we can see in the diagram here, all of the particles are forced to come into contact with each other. This is going to result in a greater pressure because we have more forces being applied over a smaller area, right? Force divided by surface area. Here we have a smaller surface area and greater numbers of forces. Therefore, we have an increased pressure. By modern understanding, by quantitative understanding, we can also rearrange these variables into an equality. So we know that based off of Boyle's experiments and the conclusions that he drew, namely his fundamental underpinning conclusion was, well, if alchemy doesn't predict the right answer, therefore alchemy must be wrong, and we need to further understand what's going on with these gases, what's going on with this atmosphere, what's going on with the air. And so he continued to study the relationship between pressure and volume and found consistently that pressure is proportional to the inverse of the volume. If you decrease the volume, you must increase the pressure. If you increase the volume, you must decrease the pressure. This is a relationship that is always true. This is because as you, again, decrease the volume, you lead to a decrease in the surface area, greater number of forces, and therefore a greater pressure. Now, if you consider two different combinations of pressures and volumes, like for instance, a container that the temperature has not been changed, the number of particles inside have not changed, like we can see illustrated here, the pressure and the volume for the first container listed here on the left must be, or rather the product of the pressure and the volume for the container here on the left must be equal to the product of the pressure and the volume for the second jar here on the right. Hence the equation P1V1 is equal to P2V2. So if we know the pressures and like only one of the volumes, we can find the missing volume, etc. Like whichever one of these variables ends up being an unknown, but we know the others, we can use this equation to determine our missing variable. We are not going to work through any specific example problem pertaining to pressures and volumes quite yet, but using the equation is pretty straightforward, and so we're just going to move on to the next of the gas laws. All right, the next gas law, published in 1702, is known as a Montan's law. This sometimes is also known as Gay-Lussac's law. I'm going to be referring to it as a Montan's law. A Montan followed in Boyle's footsteps, literally studying his publications on the relationship between pressures and volumes of gases. A Montan wanted to understand what the relationship was between pressure and temperature, since Boyle had stated that his experiments all took place at constant temperatures. What happens if you vary that? What a Montan found is that the decrease in temperature led to what we now understand is less molecular motion, but he found that it led directly to a lesser pressure. So this description of less molecular motion is more of a modern means to understand a Montan's law. A Montan more specifically was observing the relationship between temperature and pressure, and that the two were directly related to one another. So greater temperatures led to greater pressures, lesser temperatures led to lesser pressures. And in much the same way as the like Boyle's law was constructed, which Boyle's law is most consistently represented as P1V1 is equal to P2V2, a Montan was also able to put together a pretty consistent relationship. If you have two different like data points, but they pertain to the same container, same stuff is inside, and at this point we are now working at the same like volume of the container as well, you increase the temperature, we're going to see an increase in the pressure between our two different data points. So P1 divided by T1 is equal to P2 divided by T2. So if we have a container, it's just sitting at room temperature, it's going to have a certain pressure, we'll call that pressure 1 at temperature 1. If you add a little flame underneath or something to increase the temperature to T2, we're also going to see an increase in the pressure to P2. Next, our last but not least of the early gas laws that we're going to discuss is known as Charles' Law, which was discovered or published in 1802. Now notice that there is a pretty large gap in time between a Montan's law, just to go backwards, which was published in 1702, and Charles' Law, which is published in 1802. There's a 100-year gap, right? So Boyle and a Montan were working in a pretty early era of science, and both Boyle and a Montan had, let's say, the means to construct the apparatuses that they needed. They were able to like study whatever they wanted to study just due to their social status and due to their wealth. Between 1702 and 1802, there was plenty of other science happening. It's just that the gases kind of ended up going on the back burner due to limited technologies and the means to study them. It wasn't until Jacques Charles in the late 1700s leading into the early 1800s that we were able to return to the gas laws with the invention of more accurate thermometers. And so Charles wanted to round out the trifecta. If we had studied already how pressure and volume are related, as well as pressure and temperature, why not study how volume and temperature are related? And that's exactly what Charles did. He found that decreasing temperature leads to, and again, this in parentheses is more of our modern rationale, but decreased temperature leads to less molecular motion, since temperature is directly proportional to molecular motion. If you have less molecular motion, you have to also have less pressure, which is what we've already seen, and this lower pressure leads to a lesser volume. So the relationship between temperature and volume is connected because they are both related also to pressure. And if you were to increase let's say the volume of your container, you're going to increase the temperature as well, assuming pressure is remaining constant, right? So that's the tricky thing here in understanding Charles' Law. We have to assume that pressure is remaining constant here. So the relationship between two different data points, we can see as well that volume of one divided by temperature of the same one is going to be equal to volume 2 divided by temperature 2. And the easiest way to understand or visualize Charles' Law is if you've ever owned a car or have especially owned or driven a car in like the Midwestern winter time, you'll probably notice that your tires, as soon as it starts remaining consistently cold, drop in pressure and you might even need to get them filled. This is because gases inside of a container, like a balloon or a tire, are dependent, like this volume is dependent on the temperature of the world around it. So if it's summertime and you've got a really nice hot temperature, the volume of your tire is going to be pretty consistent. As soon as the temperature, though, around your tire begins to drop, the volume of the gas inside is going to drop due to that lesser molecular motion. This is going to end up giving you a flat tire if you don't add some more pressure, if you don't add some more gas to the inside of that tire. And so we can predict specifically or quantitatively the volumes and the temperatures involved using Charles' law. All right, something else that's pretty awesome, that's pretty cool, pun intended, that resulted from Charles' law being developed and studied was the discovery of absolute zero in 1848. So we're jumping ahead a little bit in our timeline just to talk about absolute zero because it is directly related to Charles's discoveries. So absolute zero was discovered by a man named William Thomson, also known as Lord Kelvin. So he was also a member of like English nobility. He had a title. He was the Lord of Kelvin. This is where we get the unit of Kelvin from. The unit of Kelvin is named after the man who discovered absolute zero, since the Kelvin scale is the absolute scale for temperature. What Thomson did was study the temperature and volume relationship of gases and graphed them. So we can see all of these data points presented here correspond to the volume versus temperature, and he was measuring at first temperature in degrees Celsius. And so we can see that there is a linear relationship between these two, and the linear relationship is the result, again, of Charles' law. V1 divided by T1 is equal to V2 divided by T2. If we drop our temperature, which moves along the x-axis, we can also see that we are linearly dropping our volume. And we keep doing that across this graph, dropping temperatures, dropping volumes, until we can see that the data points end at around this point here. Well, this particular gas that was being studied turned into a liquid at negative 100 degrees Celsius, which means you had to stop the study, right? You can't have a gas law study on a liquid, it doesn't make sense. But what Kelvin realized is we can draw a line between all of these data points and extrapolate the rest of the missing data. So Kelvin was able to determine, hypothetically, the theoretical lowest temperature that can occur by extrapolating volume versus temperature measurements down to zero volume. What this particular data point signified is if you, allegedly, right, have zero volume, there is no gaps between your particles. Everything is as smooshed together as it possibly can be, and if we are working truly at zero volume, this must mean, right, zero volume means no space, which means there is no space to move, which must also mean you have no temperature. Since temperature is related to molecular motion, which by the time Lord Kelvin was working, we understood this relationship in a vague sense, if there is no molecular motion, you can't have temperature. You can't have a meaningful measure of temperature. Therefore, at zero volume, we must also have zero Kelvin, zero temperature, the point at which temperature becomes nothing. And so the conversion between Celsius and Kelvin comes directly from this discovery. Zero Kelvin was found to intercept on the x-axis of this graph at negative 273.15 degrees Celsius. So this is where our temperature conversion between these two different scales comes from, was the discovery of absolute zero through extrapolating from gas law studies, specifically Charles' law. All right, in returning to our gas laws, though, it's time to combine them together, since it seems that pressure, volume, and temperature are all connected to each other in a really consistent way. We can rewrite or combine each of these gas laws together into what is known as the combined gas law. P1 times V1 divided by T1 is equal to P2 times V2 divided by T2. And so this gas law, or in this gas law, using this gas law, we are now changing pressure and volume and temperature. The only thing that we need to keep consistent is number of particles inside. In other words, we need to make sure that we are working with a closed system in order for the combined gas law to be a useful equation, which fortunately, with most of the gas law studies, we are working with closed systems, and so we're able to use this combined gas law pretty easily. So let's do that. Let's round out today with one last example problem pertaining to how we use these gas laws. And we're going to be just going out with a bang with the combined gas law. All right, so in this picture, to lead us into our example problem, what we have pictured here is a weather balloon. If you've never seen what a weather balloon looks like, they are fairly large. They look almost like a hot air balloon, except they are not open, right? Again, this is closed. This is one closed balloon. We can also see that there's a little parachute here and a little thing attached. What this thing is meteorological equipment. Normally, weather balloons will have some piece of equipment attached to them. They rise up into the upper atmosphere, and they are literally designed to expand to a particular point and then pop. And after the weather balloon pops, the meteorological equipment will fall and measure atmospheric and meteorological data points as it does. And the parachute will make sure that it doesn't just like crash onto the ground and we lose everything that we are trying to gather. All right, so our example problem then pertains to the popping of that weather balloon. A 100-liter weather balloon is designed to rise 30 kilometers in the air, burst, and then release that meteorological equipment back to Earth. It's like a tongue twister. As the balloon rises, the temperature is going to drop from room temperature, 20 degrees Celsius, to negative 45 degrees Celsius. And the pressure of the atmosphere is also going to drop from 255 torr to only 28 torr. What is the volume of the balloon just before it bursts? All right, so I'm gonna let you guys take these data points, plug them into our combined gas law equation, calculate this volume for yourself, and I'm gonna give you a little bit of a hint here. There was a deeper reason why we introduced absolute zero. Pay attention to your units and also pay attention to your resulting volume. The volume should not be negative, as negative volumes do not exist. All right, I'm gonna let you kind of digest and ponder what that means, try out this problem for yourself, and then we're gonna come back together and see how the numbers play together. All right, it's enough time to work. Let's come back together. P1 V1 is P1 V1 divided by T1 is equal to P2 V2 divided by T2. This is our combined gas law. This is what we're going to be, this is the equation we're going to be using to calculate what our final volume is. All right, so let's inspect our data as we plug it into this equation. We're just gonna work our way through the problem. So our first data point we can see is 100 liters. This is going to count as our V1. We know what the volume of the balloon was before it left, and we're trying to figure out what the volume is as it rises to 30 kilometers. Now we can see in this equation there is no distance measurement. This 30 kilometers is just extraneous information. It's cool to know, but we don't actually need it for the calculation. All right, as the balloon rises, we can see that the temperature is going to drop. So we have a T1 and a T2. Right before the balloon leaves is going to be the data point of 1. 2 is as it's up in the upper atmosphere right before it's about to burst. Pressure, we can see that there is a P1 as well as a P2. Before plugging these data points just willy-nilly into the equation, it's always an excellent idea to consider what the units are first. All right, and I did give the hint before letting you guys work that there was a reason why we considered absolute zero. And the reason why is whenever you are using any type of gas law equation, we need to be on an absolute scale. There needs to be a point with which your measurements can hit zero. So for instance, volume. There's no such thing as a meaningful negative volume. It doesn't make any sense. The smallest volume something can be is 0 volume, which means it literally doesn't exist. So 0 volume will be the absolute 0, and we scale upwards from there. You can always have a greater volume than 0. Same with pressure. There is a such thing as 0 pressure. There is no such thing as a negative pressure unless that negative sign is directional. But there's no such thing as an inherently negative pressure. So every pressure unit already also exists on an absolute scale. Temperature is the only tricky thing, because we can see that T2 here is a negative temperature. What it means is that this negative sign numerically is going to mess with the rest of our data points, because there is no such thing as a negative volume, there is no such thing as a negative pressure, so how are we going to cancel out this negative temperature? Doesn't make sense. So anytime we are working with the combined gas law, with Boyle's law, with a Montan's law, with Charles' law, or any of the gas laws that we have yet to see, we need to convert to Kelvin. We must convert to Kelvin, otherwise we are not working on a zeroed temperatured scale. The Kelvin scale literally does not have any negative temperatures. Everything on the Kelvin scale is positive. So this is the way that we can convert, or this is the way that we can remove that negative sign by converting into the unit of the Kelvin. So if we convert into the unit of the Kelvin, our T1 is going to be equal to 293.15 Kelvin, and our T2 is going to be equal to 228.15 Kelvin. Now these numbers are larger, but that's totally fine. The negative sign has been removed, and both Celsius and Kelvin have the exact same scale to them. Right, so the tick marks in between 1 Kelvin and 2 Kelvin is the same as 1 degree Celsius and 2 degrees Celsius. They're spaced the same. All right, that tangent, but necessary tangent, out of the way, we can now take our data points and insert them into our combined gas law. Pressure 1 is 755 torr. Volume 1 is 100 liters. And our temperature 1 is 293.15 Kelvin. And again, each of these data points here is on an absolute scale, so we don't need to worry about converting torr, we don't need to worry about converting liters. All right, on the right-hand side, our pressure is going to be 28.0 torr. Our volume is the question mark, right? We want to know how big this balloon gets right before it pops. And the final temperature is 228.15 Kelvin. Again, absolute scale is going to be absolutely necessary here. Algebraically, it's pretty easy to rearrange this equation now that we have plugged all of our variables in a meaningful way. Our second volume is going to be 2.1 times 10 to the 3 liters. That's 2,000 liters. To wrap your head around approximately how large 2,000 liters is, this is 1,000 2-liter pop bottles, right? So if you've been to the store, you can see all the pop bottles kind of arranged on the shelf. This is 1,000 of those. So this is a huge balloon, right? It's pretty easy to forget how large these weather balloons can get. So anytime there's, let's say, for instance, I'm sure you've heard the stories of oh my gosh, UFO was spotted, but then some government official is well, it was just a weather balloon. It's suspicious to hear that every time, but also keep in mind that these weather balloons in the upper atmosphere are definitely something that you can see, but they're so far away that it's too hard to make out what they are. Now, I'm not necessarily saying that every case of it's a weather balloon was true, I can't back that up, but it is a pretty reasonable thing to consider when you know how large these weather balloons can get in the upper atmosphere. All right, so this is our considering of weather balloons and also working through a calculation of the combined gas law, but the same rationale can be applied to any of the lesser or smaller gas laws like Boyle's law, Charles' law, and Montan's law. You're gonna set up the problems in the exact same way. All right, so that brings us to the end of our conversation of gas pressure and the early gas laws. Here we have some example problems, so if you would like to get some more practice in with pressure is equal to mass times acceleration divided by area, or any of the gas laws, including but not limited to our combined gas law, which is P1 divided by, or P1 times V1 divided by T1, P2 V2 divided by T2. Here are some suggested problems that I would provide to you. As always, if you have any questions and you are in my class, please do not hesitate to email me to clarify up any confusion. If you are not in my class, feel free to leave a comment in the section down below. If you have homework, please do your homework, and until next time, class is dismissed.